Good afternoon, students. So in the today's class, I'm going to revise the chapter solid state. Okay. So in that solid state, as exam orientation, what are the important questions, please? And write again. Calculation of number of atoms per unit cell in PCC, FCC, SCC and ECC. So this is important for our 2 marks. Okay. Next. Difference between crystalline and amorphous solid. Okay. Next, difference between Winkel and Schottky defect. Difference between Winkel and Schottky defect. Next, packing efficiency of BCC, FCC and SCC. Packing efficiency of BCC, FCC and SCC. Next, problems based on formula D is equal to ZM divided by AQ NA. So these two are for 3 marks, these 3 for 2 marks. Another one that is exceptional. There may be a possibility of asking question in this topic or may not. Okay, these are all important. Exceptional is, that is electrical and magnetic property of solids. There may be a chance of arising questions from these topics. It is not 100% compulsory. There may be a chance at them. Okay. Next, this one, difference between N-type and P-type. Semiconductor. Difference between N-type and P-type semiconductors. Okay. So this is all about the important questions. We will discuss one by one. Note on this, these are the only questions important for examination in preparatory you may take or in the annual examination. Only these are important. Among these topics only the questions will arise. Okay. In that 3 marks, this one is compulsory. Okay. And this one is also 3 marks. Among these two, any one is compulsory. Among these 3, any one is compulsory. Okay. You know the total chapter carries 7 marks. Okay. In that 7 marks, 2 marks question is there. That is question number 11. 2 marks question, that is question number 11. And 5 marks question, that is question number 27. Okay, in this 3 plus 2 is there. In this 3 plus 2, from this packing efficiency or from this problem. 2 marks, either the problem or any of this. And for 2 marks, any of this. Okay. So this is important. So we will discuss one by one. Start with the packing effect study. Number of unit cells per atom. The number of atoms in the respective unit cells like SCC, SCC and all. First one, number of atoms per unit cell in SCC. That is simple cubic cell, or you may also say it as primitive cell, primitive unit cell, or cell. Okay. So first I write the diagram, students. There is no need to write the diagram, calculate the number of atoms per unit cell. But for your understanding, I will write the diagram. But in the examination, you need to write. Okay. So here, this is the 1 unit cell. Primitive means the constituent particles present at the corner positions is called as what? Primitive unit cell. The constituent particles only present at the corner positions. So next, so here total number of corner number of atoms in corner is 1, 2, 3, 4, 5, 6, 7, 8. Okay, total 8 atoms are there. Understood? So here consider this one. Okay, then extend the unit cells. For this, this is 1 unit cell. Next from the same point, correct? And here it is. Extend it here. This is here. This is okay. Next, the second unit cell is from here it is. Okay. So 1, 2, 3, 4 units cell in the same layer. Okay. Similarly, above layer is in, I will assume this is 1 means in the same layer 4. 1, 2, 3, 4. In the adjacent layer. Understood? So in the above layer again 4 unit cells. 4 unit cells from same layer. Okay. Again in the backward you assume means 4 unit cells in above, below or adjacent layer. Okay, so in this side 4, in the above side or the below side, whatever you assume, so another one is there. Understood? So total, the 1 atom is shared between 8 unit cells. Okay, 1 atom is shared between 8 unit cells. Then number of atoms per unit cell is how much? So 8 atoms are there. Are you missing? 1 atom shared between 8 unit cell. So for 1 unit cell, how much? This is x. Okay. So that is x is equal to 1 divided by 8. So x is equal to 1 divided by units. So we have to calculate the number of atoms per unit cell. This is 1 unit cell. Total number of atoms is 8 divided by 1 by 8 means that is 1. This is the thing. This thing is not to write in the examination. This diagram and this everything I wrote you for your convenience, that you have to understand how the one constituent particle, how we take 1 by 8. So 1 atom is shared between 8 unit cell. So number of atoms per unit cell is 1 by 8. Okay. Like that, total 8 atoms are there. 1, 2, 3, 4, 5, 6, 7. Each atom is shared between 8 unit cell means 8 into 1 by 8, that is per unit cell we have 1 atom. Okay. So I'll write it directly. I hope you understand this diagram. So in the examination you have to write only this much. So the number of atoms per unit cell in SCC. So the number of atoms contributed from the corner position. How much? That is equal to 8 into 1 by 8. That is equal to 1. This is the calculation part. Okay. I may write like this. To write only this much. That is equal to 8 into 1 by 8. That is equal to 1. Okay. Therefore, number of atoms per unit cell in SCC is 1. If you wrote this much, student, you will get 2 marks. Diagram is not necessary. Understand? Diagram is not necessary. You have to write only this in the writing. The number of atoms contributed from the corner position is 8 into 1 by 8. That is equal to 1. So in the primitive unit cell, only at the corner positions the constituent particles are present. Okay. There is no need to addition of the extra atoms. So the number of atoms per unit cell in SCC is 1. Okay. So next one is the number of atoms per unit cell in BCC unit. BCC means body center unit cell. Okay. So here the diagram for this body center unit cell I write. Okay. Body center means one extra constituent particle is present at the center of the unit cell along with the corner positions. Body center means the constituent particles is present at the center of the unit cell along with the corner positions. Means it is a primitive unit cell along with that one extra constituent particle is present at the center of the unit cell. Okay. So if we know that this one unit cell, the one atom is shared between 8 unit cell means per unit cell 1 by 8. So if you consider this center, one extra constituent particle is there, correct? So if you write this, or if you extend this unit cell, okay, here this unit center, okay, that is how much? Only one atom per one unit cell. That means 1. 1 into 1 is 1. So this is 8 atoms. Number of unit cell is 1 by 8. That is 1. one atom per one unit cell means 1. Okay, so total number of atoms per unit cell in PCC is 1 plus 1, that is equal to 2. Total number of atoms per unit cell in PCC is 1 plus 1 is equal to 2. Okay, if you wrote this much, you get 2 marks. No need to write the diagram. Okay, next one is number of atoms per unit cell in FCC. FCC means phase center. FCC means phase center. Okay, so here I take so students listen here. Here what is phase center means the constituent particles are present at the each phase of the unit cell, center of each phase. So one cube is there. Total how many phases are there? 6 phases. So this is left, right, above, below, front and back. Total 6 phases are there. So what is phase centered unit cell means the constituent particles are present at the center of each phase along with the corner position. So here this is above, this is below, this is left, this is right, this one is front, this one is back. Total 6 atoms are present at the 6 phases of the unit cell. Okay, so here listen. Here if I consider the phase A, B, C, D. Okay, this phase is common for both the unit cells, correct? Okay, so this is the common, this is unit cell 1, this is unit cell 2. So ABCD is the common phase for both unit cell 1 and 2, correct? So in that case, what happens? So one phase centered unit cell is shared between how many unit cells? 2 unit cells. Okay, so here listen, at the corner positions already the constituent particles are there. The first sentence follows the same thing. The number of atoms contributed from the corner positions is 8 into 1 by 8 is equal to 1. Okay, that is fixed for all the unit cells because all the unit cells at corner positions, corner constituent particles are present. Okay, if we consider phase center means, so listen, here we are considering what? Number of atoms contributed from phase center. Here what happens? Total how many number of atoms are there? From 6 phases means 6 atoms. So each atom is shared between how many unit cells? 2 unit cells. So that is 1 by 2. So 6 into 1 by 2, that is 3. Okay. So the total, the number of atoms per unit cell in FCC is 1 from the corner position, 3 from the phase center, total 4. 1 plus 3 is equal to 4. That is what the number of atoms per unit cell in FCC. Understand? So the next one. ECC means end center. Okay. So students, what is end center unit cell means? It is also equal to what? Phase center only. But and right. If you want to write end center means, so this is the constituent for our unit cell. So at the corner positions, constituent particles are there. Understood? So first sentence follows the same. Okay. So next, what is end center means? I told 6 faces are there. So end center means 6 faces for 3 opposite faces. Front, above is sorry. Above and below is the one face, one opposite face. Left, right is one opposite face. Front and back is one opposite face. So in this, students, at any one of the face, opposite face, the constituent particles are present. Among 3 opposite faces, at any one of the opposite face, the constituent particles are present. That means, so it is shared between again, this is shared between how many units? So this A, B, C, D you consider means it is also shared between 2 units. So the total number of atoms in contributed from end center is total number of atoms is how much? 2. So 2 atoms are there. Per unit cell, that is 1 by 2. Correct? 2 into 1 by 2 is 1. So the total number of atoms per unit cell in ECC is 1 from the corner position and 1 from the end center. Total. Understood? So if you wrote these things, then you will get complete marks. Okay? So this is all about the number of how to calculate the number of atoms per unit cell. Okay? Only that BCC, FCC and SCC is important. This ECC exception. Most important is BCC and FCC. Understood? Okay? This is all about the units. Second one is difference between crystalline and amorphous solid. Second question, that is difference between crystalline and amorphous solids. Okay. First I will write the structure of crystalline and amorphous, then you came to understand. Okay. This is one type of atoms. This is a typical representation of a crystalline solid. Okay. Next, at the same time, consider particles are there. This is irregular arrangement. So this is which type of solid? This one is amorphous. Okay. So students, the figure itself says if this is a crystal lattice, the complete solid, here in the entire crystal a long-term regular arrangement is there. Here everything represents what? Hexagon structure. So in the entire crystal, same type of a regular arrangement and an order arrangement is there. So here this is amorphous means in the structure only we can easily observe. Here irregular arrangement is there. So the first one is, here it is crystalline, here this is amorphous. Okay. Students, same time, the first one is crystalline solids are, don't write this student. These have long range regular arrangement. These have long range regular arrangement. So this one, they have irregular arrangement or short range regular arrangement. They have irregular arrangement or short range regular arrangement. Okay, this is the first difference. Next, second one. Listen, as we compare to this structures, this one is an isotropic in nature. This one is isotropic in nature. What is the reason for anisotropic and isotropic means? Listen, if we use a thermal conductivity example, you take thermal conductivity, heat. In that thermal conductivity, consider this space, that is direction A. Okay, again consider this, that is direction B, or consider this one, that is direction C. Okay, here you consider this direction A, direction B, and direction C. Okay, so from here students, here in the direction A, total number of atoms is 1, 2, 3. 3 atoms. Correct? In direction B, here, so 1, 2, 3, 4, 5 atoms. Correct? In direction C, 1, 2, 3, 4 atoms. So thermal conductivity or we may take electrical conductivity. So electrical conductivity done by 3 atoms, 4 atoms and 5 atoms means this one shows high electrical conductivity compared to this and this. Correct? So that's why if we calculate a refractive index or a thermal conductivity, electrical conductivity, the melting point, boiling point, whatever it may be. So then what happens? They have different values at different points or at different directions, especially physical properties. Okay, like refractive index, and also refraction, like that of properties. If we measure in different directions, means we will get different. ISO means same, and ISO means different. Why it is called as aniso means because at all the directions we got different physical values or values for physical quantities. So in amorphous what happens? It is called as isotropic because so listen here we have 1, 2 atoms. In direction A we have 2 atoms. In direction B also we have approximately 2 atoms. Correct? So in direction C there is no atoms. There is no conductivity. So students here what happens? We don't know where the atoms are arranged. Here proper arrangement is there so we can easily measure. But here proper arrangement is not there and we don't know where the atoms are arranged. So at that time what happens? In all the directions we got almost same value. Not exactly same, almost same value. That's why this is called as isotropic in nature. So second one is this is very important thing, anisotropic in nature. These are isotropic in nature. You have to write isotropic in nature, anisotropic in nature. Okay? So this is isotropic and anisotropic nature. So the next one is if we come to melting point. Okay? So if we come to melting point, students, the best example is the diamond. Okay? So diamond, if consider here 1 kg of diamond is there. Okay? Here 1 kg of diamond is there. So when its melting point is 5000 Kelvin. Okay. So students, when the temperature reaches 5000 Kelvin, no matter whether it is 1 kg, 1 gram or 1 ton, we don't bother about that. This complete mass immediately melts and become liquid. Okay, so at exact 5000 Kelvin, the complete solid convert into liquid. Okay, it has a short melting point. If it is 4500 degrees Celsius, then what happens? That complete 1 kg of diamond remains solid only. When it reaches 5000 and above, then it complete mass, solid mass convert into a liquid mass. So it has sharp melting point. Okay, so here becomes the best example is plastic. So if we keep on eating plastic means it never melts suddenly. Okay, so it gradually melts, means it starts melting at 60 degrees Celsius, means it completely melts at 70 degrees Celsius. Means here it is a plastic, means first we supply some amount of temperature here, then only this portion starts melts like this. This becomes liquid. Correct? So at 60 degrees Celsius it starts melts, means at 70 degrees Celsius it completely liquefies. Okay. So here the melting point, or you may write there is no sharp melting point. They don't have sharp melting point. Okay, students. So next, this is our good one, melting point. If we observe cooling curve, okay, I told you. So this solids, crystalline solids melts at a particular temperature. If we start observe cooling curve with respect to time, this is time, this is temperature. Okay, this is 5 minutes, 10, 20, 30. Okay, so then what happens? First, the temperature of the liquid decreases and again remains constant for a certain time and again decreases. Okay, so this is one, this is one. Two breaks they have. This constant time is called as time of crystallization, where the complete liquid solidifies. Okay, so in this cooling curve, they have two breaks. If we consider amorphosis as it gradually melts, similarly it gradually decreases. Okay, it has a smooth curve. It has two breaks in the cooling curve. So here they have, they show two breaks in cooling curve. Okay, next they show smooth cooling curve. They show smooth cooling curve. Okay, next here they have definite heat of fusion. Means at certain definite heat of fusion means they release or they absorb some amount of heat when they crystallizes. Or release or absorb, that depends on what? Whether it is endothermic or exothermic reaction. Okay, so they have definite heat of fusion means of course they don't have definite heat of fusion. Okay, students, the next thing is if we cut the solid here, we get equal halves. Correct? If we cut this crystalline solid, we get equal halves, and all the surfaces are symmetrical. The cutted halves surfaces are what? Symmetrical. Means this one they have symmetry. Here you cut means you don't get symmetrical. Here you cut means this part is different, this part is different. So this is they have symmetry. They are unsymmetrical unit. They are symmetrical and they are unsymmetrical. And last one, you simply write example for crystalline solid, NaCl and diamond and quartz are the example. Okay, for this plastic, rubber, glass is the example. Okay. Another one you may write, students. These are crystalline solids are called as true solids. The amorphous solids are called as pseudo solids. Understand? So this is all about the difference between crystalline and amorphous solid. Next one is difference between Flinkel and Schottky effect. Okay. So for this also, write the diagram. Flinkel, Schottky. This is one crystal lattice. The different arrangement is there. Okay. This is the science. That is cations. This is positive. The next one is negative ions that are in bigger size. Why? Because anions are greater in size, cations are smaller in size. You know that. Correct? So this is equal number of cations and anions. You will write here plus charge. Okay? Here also this is minus. Okay? So here what happens, students? Write it here. You make out confusion. Okay, this is the equal number of cations and equal number of anions are there. So in Flinkel and Schottky defect, what happens, students? Here the cations are smaller in size. They dislocated from the original site and they are occupying any interstitial site. What happens? Dislocation of cations takes place. Why only cations takes place? Because they are smaller in size. So in Schottky defect, you write, sorry, in Flinkel, and this one is Schottky. Okay, in Flinkel defect, dislocation of cations takes place. Correct? here complete missing of cation and anion. So here, if one cation missing takes place means one anion. Here one cation is, here one anion. Okay, so here in Schottky, missing of equal number of cations and anions takes place. Reason for missing of equal number of cations and anions is to maintain electrical neutrality. If plus charge is more, then also it affects. Minus charge is more, then also it affects. So to maintain electrical neutrality, this equal number of cations and anions takes place. Here only displacement, here missing. Okay. So next, if we consider density, due to the only interchange of the ions from one position to another position, but the number of ions present per unit cell or in a crystal remains same. Okay, so that's why here density remains same. Why the density remains same? Only dislocation of ions takes place from one position to another position, not missing nor addition. Understood? Here complete missing takes place means number of ions decreases. So density is directly proportional to what? Mass by volume means density is directly proportional to mass. If mass is same, density is same. If mass is less compared to that, then what happens to the density? Decreases. Understood? So here density remains same, here density decreases. Next, so as I told you, here dislocation takes place means cations must be in small size. This one is large size. Anions are in large size. So the wrinkled effect, this effect observed in species with large size difference. Large size difference. So this one missing of complete cations and anions takes place means there is this effect is observed in species with small size difference. Okay, so last one is example, that is ZnS, AgBr, AgCl, AgI, etc. Here, this one, cations is the smallest size. This is large size. ZnS, AgBr, AgCl, and AgI. So this one, NaCl, MgO, MgCl2, okay, AgBr. This AgBr can have the capacity to show or ability to show the wrinkled effect as well as Schottky defect because it has an appreciable size between large and small. Okay, so this is all about the difference between Frinkel and Schottky, and this is very important for 2 marks. Okay, in today's class I explained total 6 marks topic, students. In the tomorrow's class I will explain packing efficiency and also that some problems regarding that formula D is equal to Zn divided by A cube. Okay.